I tried hard to be here with you in person today, but I gave United Airlines 6 chances to get me there, but the Boston storms had their crews and their logistics beat. But I love to be there in person because I want to meet the upcoming contributors to high-performance computing and computational science and engineering. It's my pleasure at least to be here virtually as a backup. I hope that you've downloaded the PDF of the slides in case our video link becomes iffy. My PowerPoint makes use of animation, and I hope to synchronize my presentation with the audio using the screen share. I've participated in every AT-PESC so far since 2013, but always on the topic of scalable solvers. I used to run DOE's lab university infrastructure group for scalable solvers, about which you've heard several on August 6th, such as PETSI, Hyper, SuperLU, Sundials, and Trilinos. My group at KAUST also works primarily on scalable solvers. We employ 2 PETSI contributors, and we have made many contributions to hierarchically low-rank software for high-performance computing, in particular for GPUs. However, my topic to cover today for this AT-PESC is a topic on the minds of nearly everyone in HPC, from hardware, software, algorithms, applications, and workforce management, and all of these combined. And it's the subject of DOE workshops and NSF Institute workshops in the USA, and a consortium of the G7 nations that operate most of the world's supercomputers, in which I also participate, on big data and extreme computing. It is the topic of convergence, and 2 of the main streams of computing, large-scale simulation and big data analytics. And of course, it includes a healthy measure of artificial intelligence. So I'll switch to screen share and go to my title slide. But before I move on to the talk, I mentioned my current affiliation at King Abdullah University of Science and Technology on the Red Sea. KAUST is a hybrid between a U.S. national lab and a university. It employs about 1,200 graduate students and about 1,000 postdoc research scientists and faculty working on challenges in energy, environment, food, and water. More than half of the research groups use supercomputing, and our supercomputer is usually in the top 20, although currently it is number 36. But we have it to ourselves, which is nice. Our new president, Tony Chan, is well known to some perhaps, as director of the Math Sciences at the National Science Foundation. He also started the NSF Math Institute at UCLA when he was a professor there. So it's the first time I've had a president who's a computational scientist, and I wonder how many of you can say the same thing. This is the logo of our university. Some people say it stands for energy, environment, food, and water, but I say it stands for the 4 ways of knowing. Theory, going back to the Greeks, millennia old. Experiment, going back, let's say, at least in Western traditions, to Galileo. And of course, the convergence of theory and experiment gave us modern science. Then we have simulation coming around in the 1940s and 50s at Los Alamos with the earliest stored program digital computers, maybe decades old. And now we have big data, maybe a decade or so old.
David,
the first 2, of course, are pre-computational.
David, can you hear me? We don't see your slides. Can you try sharing again the...
Yes. Okay, I guess you have the slides, but...
yes, well, we don't see your PowerPoint.
Right.
Now.
No, I mean, I want to follow them by animation. Is it available now?
Yes. You have to put the full screen.
Right.
Perfect.
Okay.
Thanks so much.
Great. Thank you very much for that interruption. I'll try to be audio cued in here. So these are the animations that I just had finished. Of course, these 4 paradigms are now well known. They're the subject of popular science books. And what we're interested really in is this second convergence. If the first convergence gave us modern science, what will the second one give us? And we believe, of course, being in the Davy tradition, human predictive tools to overcome all the great natural and technological challenges that we face. Now, the convergence paradigms has been pursued for a number of years by this BDEC consortium, and in 2018, a write-up of sorts appeared in the International Journal for High Performance Computing Applications, but you can download any and study minutes of these meetings at exascale.org. And this is the successor to the 2011 International Exascale Software Roadmap, where the countries that primarily in super extreme scale came together and said, hey, it's going to be a real challenge to port all this open source scientific software. We should tie up and coordinate this. Now, BDEC 2 started recently, and this is in recognition of the fact that a lot of the big data that we work with comes from the edge, from satellites, from internet logs, from different sensors, from many different laboratories, biomass data that is then federated. And a lot of this edge data, beamlines, for example, at national labs, it's too large to collect and transmit. So we need some lightweight learning at the edge to sort, to search, to learn about the distribution and the subset of the data that should be centralized. And so the edge data is then pulled into the cloud to learn, and an inference model is sent back to the edge devices. So if this interests you, look into the BDEC. It's an ongoing endeavor. There'll be machine learning in the application, of course. That's for enhanced scientific discovery. There'll be machine learning in the computational infrastructure for improved performance. Any system capable of simulating a complex system is even more complex, and you've been hearing for 2 weeks about the difficulties of mapping data to data structures in distributed memory and so forth, doing high performance I/O. These are all challenges for which there's very little theoretical guidance sometimes, but if we're going to run the same application many years, we can learn about how it runs best on a given piece of hardware. Then, as I've just alluded to, there'll be machine learning at the edge for managing the data volume. So this talk is really a tale of two communities, one of high-performance computing, which grew up around Moore's law, multiplied by massive parallelism. It's faster than Moore's law, the growth in computational capability, because of that. It has become predictive on a par with experiments. For example, there have been 2 Nobel Prizes in chemistry now that have gone to computational chemists. Prized for policy support, for instance, in negotiating treaties with nuclear weapons or climate. And of course, it's recognized for decisions where to drill an oil well, how to do personalized therapy planning, for instance, for radiation on a tumor. Then there's high-end data analytics, the other main community being drawn into this convergence. It grew up around open source tools like Hadoop from online search and service providers. It created a $1 trillion market in analyzing human preferences and learning about us. It's now dictating the design of network and computer architecture because of its economic importance. And it's a much bigger economy than that of scientific computing. So those of us who do scientific computing have to figure out how we can make use of the devices that the market produces for us. And it's now transforming university curricula and national investments. And it's migrating to scientific data, evolving as it goes. Now, when I've given this talk in the past, some people have questioned me. Really? $1 trillion market? Yes. Look at the top 5 companies in the world as of yesterday. Based on their market capitalization. You can see there that the sum of their valuation is about $4 trillion. And if you look at the projected annual revenues of these 5 companies for 2019, it will be close to $1 trillion. So it definitely dominates the scientific computing market, and we have to learn to play well with it. And I believe that, as has happened often in the past, we will actually help to lead it. Now, there's been pressure on HPC coming from the vendors, even those that are contracted from the DOE to deliver $100 million systems have to leverage their technology developments for the much larger data science markets. And this includes the exploitation of lower precision floating point, which has become pervasive in deep learning applications. Fortunately, the concerns are the same to some extent in both of these communities. They are energy efficiency, whether you're designing a huge cloud platform or a supercomputer. There's limited memory per core, which mainly is a function of the fact that it's much easier to replicate a lot of cores than it is to pay for the memory that goes with them. And as a consequence, there's limited memory bandwidth per core, which means that the sweet spot of algorithmic balance between communication and computation is shifting. There's pressure on high-end data analytics as well. Since the beginning of data has been moved primarily over stateless networks. The routing is based on address bits. There's no system-wide coordination of the data sets or buffering. There have been workarounds to cope with increasing volume, but they are now creaking. One of the interesting workarounds was done by a college classmate of mine who invented the Akamai project out of MIT a couple of decades ago to do web caching of different data sets that were in common use and needed around the world, such as the New York Times front pages or others. There are solutions for buffering massive data sets from the HPC edge, such as CERN in Switzerland, the particle collider. Many of their challenges in sharing collider data with the world's physicists are now being exploited by other users. Seismic arrays, satellites, scanning electron microscopes, laser sheets sensitivity for lab experiments, and so forth. And these scientific edge solutions will be useful, perhaps, for the fog environments of the big data cloud. Now, if you download our first report, you'll see many findings there. There are many motivations, we believe, to bring together these two large communities. And we believe they should be combined in situ, not pipe disks with intermediate files. That just leaves too many benefits on the table. The I/O is the slow partner. There are, however, many hurdles to the convergence of high-performance computing and high analytics. But ultimately, this will not be a forced marriage because of the importance of each to the other. Science and engineering may be minority users of big data today, and perhaps forever, if you consider the 7 billion people in the world generating data pertaining to the economy, transportation, and so forth. But we can become leaders in the big data community by harnessing what we know of high-performance computing and being pathfinders for other applications once again. Now, the combination of the third and fourth paradigms is actually not new. It's existed in scientific computing for a long time in a variety of specialized ways. For instance, inverse problems. On the left is a typical forward problem where you set up a model, the forcing terms, the boundary conditions, the initial conditions, and the constitutive parameters, and out comes a solution after, for example, the flash code that you've just heard Anshu describe. But in some applications, like subterranean flow or earthquake source inversion, we don't have all the constitutive parameters. They're invisible to us, but we have a lot of observations at the domain, and we can make inferences about the interior of the domain and its properties from putting sources in and studying how they come out. So this is the classic inverse problem. It's ill-posed mathematically, you need to impose lots of regularization, assumptions about the solutions in order to get good results. Now, these traditional combinations also are used in data assimilation, where we might have a forecast of, say, an ongoing hurricane or an oil spill that is regularly nudged towards reality. That is, the simulation nudged towards reality by real-time measurements. And these are some of the types of data assimilation that we do at KAUST. So my definition of data assimilation is when two ugly parents have a beautiful child. You have simulation with all of its incomplete information, and you have experimentation with all of its errors. And if you put them together, they make up for many of each other's faults. The simulation can, in some sense, regularize the experiments with known physical aspects of the model. And this is, of course, a very fruitful way that the third and fourth paradigms have been coming together for more than a decade on the scientific side. And here's a beautiful book recently authored by Mark Ash and company. Mark is the leader of the BDEC2 consortium of the European Union. If you go to that first report, you'll see a table, I believe it's table 1, and it shows how the third paradigm and the two different aspects of the fourth paradigm, namely big data analytics and machine learning, can work together. So simulation can provide or can benefit from big data analytics through steering in high-dimensional parameter space. There are many configurations we want to examine. Which ones are the most fruitful? And we can do some in situ processing. Learning can provide smart data compression, and it can even supply the replacement of models, heuristics, for example, cloud-edo in an atmospheric modeling, or the effective viscosity of eddies with learned functions. Simulation can provide to analytics a physics-based regularization among all the statistically equally probable outcomes. Which ones satisfy the conservation of energy or the conservation of mass, preserve non-negative densities, and so forth. And to machine learning, simulation can provide training sets. A lot of big data isn't really that big. For example, think of the machine learning to keep the world's largest scientific experiment, ITER, the fusion reactor being built in Cadarache, France, from destroying itself when all that energy of the magnetic field is released on an instability. We don't want to run a lot of those instability experiments. We want to simulate them and then detect when an instability is incipient in the actual device. So simulation can augment real-world data. And then, of course, the two forms of analytics, which is sort of a production level without learning, where the model stays the same as data gets ingested, and then learning where the model evolves based on the ingestion of data. These two have benefits for each other as well. So there's also the theme of convergence for performance, because it's not just the HPC application, like the climate model or the supernova model, that benefits from convergence, but it's also performance tuning of the hardware-software environment. For example, think of iterative solvers for a nonlinear partial differential equation. There are so many tuning parameters that are not part of the physics. They're part of just eking out a solution in terms of the outer Newton convergence, the inner linear solver convergence, the number of levels in the multi-grid preconditioner, the kind of smoother to use. All of these things are hard to choose from a theoretical basis, but they can be learned. Emerging architectures have complex memory hierarchies. Where do you place the data? And so forth, for which optimal data placement can be learned. So this dream appears to be practical. If we got modern science from the first convergence, and we expect many benefits technologically and socially and in terms of preserving the environment from the second, then what are the challenges that we face? And particularly the challenges that your generation of computational science faces, because you'll be expected to working across this interface. Well, we can go back to this 2015 paper in the Communications of the ACM by Dan Reed and Jack Nongera, discussing the software of the third and fourth paradigms. This slide is a little bit old, but on the left you see a typical software stack for big data analytics with codes like Scoop and Flume and MapReduce and so forth. And on the right you see the typical simulation environment, a lot of which you've been learning about this week with domain-specific libraries for applications, numerical libraries like solvers and mesh generators, and all of the infrastructure for first developing a code and then putting it into the workflow and so forth. And if you compare these two stacks, really all they have in common is Linux. And now that big data applications are going distributed, I guess you could say they have MPI in common too. But there are so many differences between these two worlds. The software stacks, the computing facilities that we're used to running them on in terms of their execution and storage policies. The research communities themselves have different conferences and use different journals. The university curricula are different between the two types of scholars being trained. And some of the hardware forcings are different in terms of the natural precisions. If you have a type elliptic problem or a biharmonic problem, those matrices are very ill-conditioned. You need at least double precision. You may need quadruple precision for highly refined meshes. Whereas for machine learning, you may use single or even half the instructions for the inner loops of those two environments. But they're divergent not only in the software stacks, but in many cultural aspects, like data ownership. In high-performance computing, it's generally private, but in high-end data analytics, it's often curated by the community. The access in HPC is typically bulk and fixed for a given time. You make a reservation on a supercomputer. For data, it's often fine-grained and elastic. The data storage in HPC is local and temporary, whereas in HDA, it's cloud-based and persistent, literally over decades. The scheduling policies primarily are batch in HPC and primarily interactive in data analytics. HPC likes to have exclusive space. HDA is happy to share space. The premiums in high-performance computing are on capability and reliability. In high-end data analytics, they're on capacity and resilience. We're primarily making statistical outcomes, and we can tolerate quite a bit more in terms of a shaky environment. With HPC, we do what are called forklift upgrades. Every 5 years, we get a new system, and it's fairly homogeneous. Well, it may have heterogeneous processors, but all 10,000 of those processors are the same as each other. And in high-end data analytics, we might, add $10 million worth of hardware every year in sort of a rotating set of upgrades and have a highly heterogeneous cloud platform. If you go back through the early slides of the BDEC consortium, you'll see the struggles that we had to work through these dichotomous backgrounds. I won't mine the history, but just sort of end up with the results. The vendors wish to unify their offerings. The original third-party vendors are now market dominated by the fourth, and under all hardware scenarios, data movement is becoming much more expensive than computation, literally 2 or 3 orders of magnitude. Simulation and analytics should be done in situ with each other rather than piped through memory, through deep memory, or through disks. By the way, we can digress onto one of the oldest forms of data analytics, which is scientific visualization. I think you've heard some about that this week. Of course, many results of simulation may be more or less valuable without fast turnaround on the viz. Sim can be expensive, and we don't want to waste an unmonitored one. We want to be able to steer it. And on the other direction, visualization benefits from HPC, because many visualization demands are now real-time or put a premium on time to solution. There may be a viz-based human decision in high performance may be required, or viz may dominate. And by the time the simulations scale, all of their global data structure kernels must also scale. And if you have meshed data, then the kind of things you want to do with it in viz may depend on some of the same linear solvers or stencil applications or graph searches or whatever. So there are a lot of synergisms. One thing we discovered in writing the first BDEC report is that there are really multiple classes of big data, and at least 3 of them are very natural in scientific big data. There's the data arriving from edge devices, often in real time, such as beamlines, that is never centralized but processed on the fly, maybe decimating by a factor of 10 or 100 what is actually stored from what is first sensed. Then there are the federated multi-source data, like in bioinformatics for proteomics or genomics, which are intended for permanent archive and are contributed to by dozens of labs around the world. And then there are combinations of data retrieved from archival source, such as historical climate data and dynamic data from a simulation. And the Pathways report addresses these challenges in customized sections. One thing I'd like to review with you is an unconventional, but I think very appropriate classification of the field of AI. This comes from Engling Go, the chief technologist of HPE, and he classifies both our world of simulation with its top-down deductive rules and the bottom-up inductive universe of big data as 2 different forms of artificial intelligence. After all, they are a machine informing us. But we'll decide well cycle of simulation and blow up a little bit more the analytics realm into that subset which is primarily predicting data itself through regression and classical statistical means, and that relatively newer form which is trying to predict categories, to do classification and clustering. Within the statistical realm, there's linear and nonlinear. Within classification and clustering are those subspecialties. Classification, of course, can be supervised if we label the data, and there are many subcategories there, including the very popular one of deep learning, which is making so many economic benefits right now, and also, we could say, political and other. And then there's the clustering, which is primarily an unsupervised attempt to make sense of a large cache of data. Well, simulation and analytics make a cute pairing. They both include both models and data. Simulation uses a model usually coming from physics to produce data. Analytics uses a model undergirded by statistics. Produces a model from statistical data. The models generated by analytics can, of course, be used in simulation, although they're not the only source and not the primary source historically. And data generated by simulation can be used in analytics, although it is, of course, not the only source and really only a fairly recent one. But between these two, a virtuous cycle can be set up. And that cycle can be put inside a black box that we could consider a future simulation system, which has data inputs that leads to predictions. Traditionally, this has been a human-engineered code that does not improve with the flow of data through it, except with the human outside the loop gradually improving the model. But in the future, these simulation systems may include a lot of internal machine learning that improves the model when we receive training data as well. And of course, we may learn incorrect things as with a child, so this requires really, of course, the custodianship of the scientist. Including learning in the loop can enhance the predictivity of the simulation, and including both data from simulation and observation in the loop can enhance the learning. So this is ultimately a win-win marriage, this in situ converged system towards which both sides are aiming. From the scientific side, you could consider this the scientific method on steroids. In fact, if you were at SC18 last November in Dallas, you would have noted that for the first time, a big data paper won the Gordon Bell Prize. The Gordon Bell Prize is about 25 years old, and it's always been won by a simulation endeavor. But there were 3 big data finalists among the 6 Gordon Bell finalists last year. They were all run on Summit, the new system at Oak Ridge, about which you've heard a great deal this week. Now, really, we have a new instrument emerging, and one way to get an insight or an appreciation of this is to go back to one of the world's greatest chemists, Humphrey Davy. He discovered a good part of the upper part of the periodic table, not because, as he says in his own words, his intellectual powers were greater than those of his peers, but because he had placed at his disposal a new instrument that he himself invented, namely electrochemistry, which enabled him to separate things in solution, allowing him to discover many of the monovalent and divalent metals and the halides. And if you go back to the periodic table, the things outlined in black are things that Humphrey Davy discovered in a 3-year sprint. That should say 1807 to 1810. And a similar sprint occurred in the 50s at Berkeley with the early cyclotrons. All these post-uranium elements were discovered not because the Berkeley physicists were better than those elsewhere around the world at that time, because they had a new instrument. And so you are coming into your scientific maturity at a time of a brand new instrument, namely the convergence of, we could say, machine learning and simulation. There are many bonuses of this convergence, one of which is rethinking scientific computing in new data types. I've already alluded to the fact that a lot of elliptic problems will never give up double precision or maybe quadruple precision because of the ill-conditioned implicit systems they have to solve. However, a lot of hyperbolic problems we're finding can be solved very well with just single precision, wave propagation type problems, Fourier type problems. This was a paper from GTC 2018 in Santa Clara by a Stanford researcher using half precision and finding that his seismic modeling results were just as valid. Here is that was of course using GPUs. An Intel researcher who reported at the Intel Extreme Computing User Group on our campus in 2018 also was doing seismic inversion and was actually primarily looking at the forward model and finding that single precision was more than sufficient, whereas double precision had always been used. Another benefit of these two worlds coming together will be in reducing the volume of what must be stored. All of your university data centers, I guarantee, without knowing where you're from, are creaking under a load of their disks being dangerously full to the point of view of reduced performance or maybe even non-robust backups and so forth. On the left is shown a diagram of jobs from 1 to 17,000 along the x-axis of a particular anonymous atmospheric modeling job that was run on several of the DOE and NSF supercomputer centers. And this was documented in a paper out of the University of Illinois by Bill Groff and company. And the simulation part of that run was the light blue at the top. The three color bands at the bottom are the percentage of the runtime that was dedicated to some form of I/O. It's always more than half. You thought you were a climate modeler doing simulation, but you were really just reading and writing from disk. And if you look on the right diagram, it's a log scale in the vertical, and it's a histogram from 0 to 100% of applications on the horizontal, showing how many of those applications are using the I/O system at any reasonable fraction of its peak. The peak is for three different machines are the three colored horizontal lines, and the applications ordered by percentage of use of peak. Remember, this is a log scale. So if you're down 3 lines, you're down by 1 billion in terms of your percentage of peak use of that I/O system. Another way that convergence is going to benefit us is in a data center economy for not just the rate at which we store data, but the amount of data that we need to store. So on the left is an uncompressed combustion field, and on the right is a compressed one. The tolerance there is 10 to the minus 4. I think both to the eyeball norm and to the uses that scientists were making of this data, it was equivalent. But on the right, although it was lossy to a 10 to the minus 4 degradation, there was a 6.4 factor of compression. You can't usually compress field data very well with a lossless algorithm like gzip. By the way, this work, like the previous work, is work being done right where you are at Argonne National Labs. This one is by Frank Capello. So some summary observations on our convergence prospect. It began as an architectural imperative due to market size, but it flourishes as an intellectual stimulus in its own right. But these two distinct ecosystems will require some of your work in blending. In standalone modes, everything is different between these two communities, but this must be overcome since the standalone mode with pipelines between may simply not be a competitive way to do science or to run a national lab. So we're trying to give convergence the edge, namely to bring in data from the edge, where, as mentioned earlier, data from the edge is sent into the cloud to learn, the inference model is sent back to the edge, and then the data can be largely reduced by the low power, low capability sensors and other instruments at the edge. So we need some very lightweight machine learning there. Why do we need it? Here's CERN. It's generating about 780 petabytes a year. That's nearly, that's just one of the instruments. That's the Atlas instrument. There are many instruments off of those beamlines. That one's generating an exabyte a year. CERN has been a leader, not just in inventing the internet about 30 years ago, but also in learning how to handle big data sets. Here's another scientific instrument that is producing, or is slated to produce a lot of data, about 31 exabytes a year to be reduced to 3 exabytes to store. This is one of the two fields of the square kilometer array, which is actually a square kilometer of sensing area. It's spread over many thousands of square kilometers of South Africa and Australia with many different types of telescopic devices. The SKA will produce annually about 6 global human DNA's worth of data. If you strung all of your data and mine end to end for all 7 billion of us, the SKA will produce more than 6 times that amount of data every year. So this is a brief description of the work of this consortium. The next meeting is in October in San Diego, and we expect to produce a report on the edge data like the mainstream big data in a year or so. So this is the baton pass that my generation is giving to yours. The third and fourth paradigms have traditionally been separate, but now they will be converged. And I'd like to use my remaining time up until your questions for a brief look at the previous G7 roadmap report, namely the Exascale computing roadmap, whose implications are now well underway in some of the soft that you've been hearing this week. We learned at that time that the Exascale architectural drivers would primarily be 3. That clock rates would cease to increase, while the arithmetic capability of individual processors would increase dramatically by flooding them with cores. That memory storage capacity would fail to keep up with that flood of cores, and that the transmission capability, namely memory bandwidth and network bandwidth between those many core processors, would fail to keep up with the arithmetic capability, undermining many generations of open source scientific software costing billions of dollars to develop. We could indeed build exascale machines, but we would only get petascale performance out of them because they would be bottlenecked in memory size and memory width. And think of 2 decades evolution from the first terascale machine, the ASCII Red at Sandia, on which my group actually won a Gordon Bell Prize in 1997 on that 1 teraflops machine, which required nearly a megawatt to operate. Well, a couple of decades later, you had that 1 teraflop in a processor you could hold in your hand and put into your laptop, and it was only costing about a fifth of a kilowatt, 200 watts. So 3.5 orders of magnitude of performance improvement from the power point of view to get the same computational performance. But this did not come without consequence to the algorithms. And here is a diagram from Karen Bergman's group at KAUST. Karen is one of the optical network experts in our field. She has normalized to 1 at the left endpoint in the year 2010. The node power in blue, which at that time was 31 gigaflops, the node bandwidth, which was 2.7 gigabytes a second, and their ratio in terms of bytes per flops, which was about 1/10, 0.09. That was in 2010, and that was for the average of the top 10 systems in the top 500 list for doing the LINPACK benchmark. As time evolved, that ratio got progressively worse. This is a log scale, and it's gotten much worse with Summit. Summit was a big kick in the face of algorithms by increasing the arithmetic capability so much, not in bandwidth nodes. So we have an order of magnitude worse in terms of the ability of algorithms to get their data than we were with Taihu Lite, which was already much worse than the situation in 2010. So this is the architectural field in which we're working, and that's actually one of the reasons why low precision is so enticing. Because if we can work with single or half precision, we're in effect doubling or quadrupling their bandwidth, not to the same cores. But it's not just the bandwidth, of course, it's the energy. Where will we get the energy? What's the carbon footprint of these new machines? To access SRAM from your CPU is about 10 femtojoules per bit. It's about 1,000 times worse in the picojoules, 100 times worse to go to DRAM on the chip. Another 10 worse to go to high bandwidth memory, and then to go to DDR3 a few centimeters away. We're talking about 10 to the 4th disadvantage in going beyond the cache, with similar ratios for latency and bandwidth. So algorithms must span a widening gulf between very ambitious applications, which want all kinds of in model and so forth, and austere architectures, which can only be used efficiently, it often appears, when things are highly uniform. So it's up to us, the algorithm designers in the middle, to make this work, and this is, of course, a deployment program for algorithm developers. As mentioned before, billions of dollars of software hangs in the balance. What software is that? Well, it's the model-related software like meshing and partitioning and doing random number generation in parallel and doing uncertainty quantification and all that stuff that the scientists know. And then there's the development-related stuff that the computer scientists help us with in terms of compilers, simulators, debuggers, profilers. And then there's the production-related software, platform, authentication, I/O, frameworks, data miners, and so forth. The high-end computers come with very little of this. It gets built by the community. My group works just on the solvers and integrators, so I hope there's a lot of you out there working on all of those other critical tools that you've been hearing about all week. When we think of embracing opportunities of the exascale, We often start with the hardware, but really it's the data structures, the task graphs, the flowcharts, the communication patterns that are the soul of these machines. This is where research needs to be done, algorithmically speaking. And the architectural imperatives that go along that lead to the next generation of algorithmic development based on those characteristics is to reduce synchrony, because with 1 billion cores, you can't wait for the slowest core to catch up. This means reducing synchrony either in the frequency with which you synchronize or in the span. It's okay to synchronize a lot locally as long as those local basins do not have to synchronize as frequently with each other. We need to reside high in the memory hierarchy, because remember that factor of 10 to the 4th from going down to DRAM. So stay as close as possible to the processing elements. This means working with small cacheable data sets and reusing that data for many operations. And then we need to build instructions that are low energy and high performance that are coming with these new devices, GPUs and many cores, the vector instructions, the tensor instructions. For example, a tensor core with one instruction, you can do 64 operations, multiplying 2 4x4 matrices and adding to a third 4x4 matrix as required in the convolutional deep learning. That operation has been made very convenient and cheap. Can we use it in our scientific codes as fluently? So in going to in implementing these algorithmic strategies, there are really, I say, 3 that you should be aiming for. One is to employ dynamic runtime systems based on directed acyclic graphs rather than the bulk synchronous model. Each operation can fire as its data operands become available. There are many examples of these nowadays: OMPSS, Quark, StarPU, OpenMP, HPX, and so forth. Maybe you've heard about a few of them at the workshop. I think you heard a lot about OpenMP earlier last week. There's hierarchical low-rank data sparsity. The curse of dimensionality is met with the blessing of low rank. A lot of data that appears big ain't so. It can be represented to high accuracy with orders of magnitude less bytes. And I'll do an example of that as I close. And then we want to code to the architecture, but present an abstract API for the scientists operating at a higher level. And this follows the Hourglass model of IP-TCP. As you know, the internet supports myriads of applications, from forecasting the weather to ordering shoes, and it does it out of arcs in many generations of it's that by having this magical interface called IP-TCP, which channels all those different applications into all those different architectures. And we have to think that way in terms of our scientific software stack as well. So let's consider these all briefly. Taskification based on DAGS. We want to remove the artifactual synchronizations that we build in when we make a subroutine boundary of the call and make sure everything is lined up before the call occurs. Or when we make a triply nested loop and force the data to be visited in the order of the incrementations of the loop indices rather than whenever a set of data is available to fire. And we have to expose more concurrency. It costs to manage the resulting task graph, and we may lose some memory locality if we fill a synchronization void by pulling in some data from somewhere else. But this is an optimization to be pursued at the billion core level. Remember, an exascale is 1 billion cores at a gigahertz, 10 to the 9th times 10 to the 9th. We want to shrink memory footprints to live higher in memory hierarchy, because that means faster and lower power. Yes, it reduces operation counts, but that's not the important thing. Operations are pretty inexpensive. We want to reduce the data accesses. And we want to be smart about our data. If we don't need high accuracy, we want to tune the work that we need to get the lower accuracy to the requirements. You can't do that with a one-size-fits-all, explicit LU solve. You have to do something that exploits the low-rank nature of in the first place. Disadvantages are paying the cost of compression, and not all operators compress well. Random matrices don't compress at all, but all matrices are a problem, matrices covariance statistics, matrices and Hessian problems from optimization, matrices from integral equations with plus-type kernels, pure complements from elliptic PDEs. These are all dense operators that compress extremely well. Then there's coding to the architecture. We get a lot of vector and tensor operations. We need to create lots of small batches that can fire from the same instruction stream to amortize the call overheads. And we need to create a polyalgorithmic approach based on the block size. If the blocks are 32 by 32, do one thing. If they're 256 by 256, maybe the exact same functional operation goes through much different algorithms of the way caches are accessible. There's all kinds of tricks here that the ninjas know in terms of non-temporal stores when writing data back down the memory hierarchy, coalesced memory accesses, double buffering. Not everybody can or should need to know those. We need to train some chemists and some atmospheric modelers, but those of us that are able to reason with the Byzantine memory systems of the Exascale need to reduce the sensitivity to misusing memory for everybody else. The code is much more complex and has to be done for every processor, but it looks the same at the higher level. That's the Hourglass. So just a few examples. Here is a generalized eigenproblem. You can think Schrodinger. A and B are full matrices. We normally will factorize B, apply the Cholesky factors to A, get a standard eigenvalue problem, reduce to tridiagonal form, and then use QR. 3 of those operations are compute intensive. They are shown stacked at the bottom, but we can merge them in one task graph, obliterating the subroutine boundaries and starting already on the second task while the first one has just left the upper left-hand corner, shrinking the sum of the heights to reduce the runtime and increasing the width to increase the concurrency that is available for this algorithm. Same arithmetic, different order, more efficient execution. We need to reduce the memory footprint with low rank, tune the block structure and length parameters to a variety of hardware. The key tool here is hierarchical matrices. We've had 20 years, they're not very important in platforms applications. We can turn an n-cubed operation into an n log n operation in terms of matrix solve for a general matrix. We know how to do that with fast multipole or a constant coefficient matrix with a Green's function. Now we have algebraically generalized that to non-coefficient types of equations. Here is the way we construct a hierarchically low rank matrix. We ask, is the overall matrix low rank? No, it's non-singular, it's high rank. We break it into subblocks. Are any of those? We break those into more subblocks in step 2. Now we'll actually go SV and rest. Then we move in constantly recursively subdividing until we're left with a red near diagonal portion, which has to remain being stored densely. But the union of these red and blue matrices gives us a highly compressed but highly accurate representation of the original. And so this is a preoccupation that our group, among many others, is working on now. And here's, of course, the Hourglass model, many apps, many architectures, hopefully a modest interface that everybody has to learn. So here is some of the software that we're developing at KAUST that we uncovered. This is a multi-objective adaptive optics controller for telescopes that are earthbound that correct for atmospheric turbulence. It's large applications have to be effectively built on a mountain with low power. So hierarchically low rank's the way to go. This is a statistics package, covariance matrices. They have to be 1,000,000 by 1,000,000. That would be, of course, what would that be? That would be 10 to the 12 trillion elements. That would be 8 terabytes stored in double precision. You know how much a terabyte is and how long it takes your computer to back up even a few gigabytes. So we have to compress that. And again, it's hierarchically low-rank matrices, but with an R interface. The KAUST is now in NVIDIA Hourglass. It's a special class of operations for dense symmetric kernels. The KAUST, it's a singular value decomposition that has much more concurrency than the traditional scale pack. It's got about an order of magnitude more operations. It's so much more concurrent that it actually finishes faster, and the operations are batchable. This is a mesh traversal operation for many core systems that has been adopted by Intel or the petroleum industry and so forth. We say a good player skates to where the puck is, but a great player skates to where the puck is going to be. At ATPESC, you've learned where the puck is going to be in terms of computer architecture, and you've learned many of the tools that will take your science to that rendezvous. In the Middle East, we don't have hockey, we have falconry. And our analogous statement is the falcon doesn't skate to where the prey is, it flies to where the prey is going to be. Here is a prey in the dashed pink dots, which is flying along. And this is what a falcon does not do. The falcon does not fly towards where the prey is at every moment. That would be inefficient. The falcon does calculate. It figures out where the prey is moving to, and it moves to where the prey will be by the time it can get there. This is an amazing discovery. It was made a couple of years ago. You can read about it in the National Academy of Sciences proceedings, but it's a beautiful analogy for what we should be doing as computational scientists. So this is the second baton pass from the bulk synchronous world that you've inherited to the energy austere world that you'll have to program. Our architecture has trickles from HPC. Exascale machine room means Exascale machine room means scale under your desk. High definition, high-end data analytics has a trickle back, as Doug Cutting said, from Google. Google is living a few years in the future, and it sends the rest of us messages. It sends the scientific community some messages about what the big data community have been doing with some data, and so we should be paying attention to those. To conclude, about an hour here, there are scientific and engineering advances that are motivations for convergence. Tune physical parameters for better performance, tune algorithmic parameters for better execution performance, filter out non-physical candidates, provide data for learning. We have economy of data center operations to look forward to, and the development of a competitive workforce, namely you. And if you look in your PDF, you can find references to the community reports, and I predict that we do not need a shotgun marriage. These two communities will merge for self-interest. And I thank you very much for your kind attention. I'm happy to take questions. My email is at the bottom of the last slide or at the tail end of your PDF deck. And if a question doesn't fit this brief period, or if you want to pursue something at greater length, I welcome that. Thank you very much.
Thank you. I'm going to pass the microphone in case there is any question from the audience. I personally have one question, but I will wait before.
Okay, and I'm trying to learn how to stop sharing. There we go. Okay. Now I think I can see the big group. Maybe.
Can you see as well?
I see a panorama of the audience, but it's a small window on my screen.
So I'm curious about your analogy with the falcon. So where do you think is our time scale in years? Where are we targeting now? Are we focusing in the machine?
Well,
do you see us focusing in 10 years or in 50? Our prey. If we can
I'm thinking, I have much more modest intentions, Marta. It's merely, you know, a sort of a plea to see where the architectures are going, to look at the fact that we're going to be invited to use more precisions than we have today. We may have processors that are less resilient than we have today because we may ask that of the vendors. We may say, yes, we know you could give us a reliable processor, but error correcting memory means I do 3 memory operations whereby I could do just 1 if I just wrote and took the chance, the very rare chance that there would be a memory write failure. Or I can have less redundancy in 3 operations and loading. So we actually ask for less resilient, less precise hardware in order to get more science done. And this means that we've been spoiled with double precision and fully reliable memory and fully reliable processors. We may be incentivized to structure our data into 2 parts. That which has to be preserved with today's level of correctness, and that which we can always recover from if it becomes corrupted. We may have our subroutines in 2 parts, that which always has to be done reliably and that which we can recover from. Example, we have a multi-grid code. We have to evaluate the residual with high accuracy and store it with high accuracy because that tells us whether we've solved the problem. But when we're doing a smoothing, if we had a spike in the data from a misread or a miswrite, then that spike would be eliminated at the next round of the next multi-grid pass. So since it will be right 99.999% of the time, we may learn to hierarchicalize our code and our processors in order to use the cheaper ones most of the time. This is just one example of skating to where the puck will be rather than to where it is today.
And one question for the audience, I was curious about how many of you are doing any compression techniques, are using any compression technique? We have only 4 out of 73, so maybe there is work to be done in that area. And I had one last question was, so are we trying to capture any prey that is out of our control? I mean, now we know some problems. Is there anything that we don't dare to try to capture because it's too big and we are kind of delaying in time to see if the machines can catch up in trying to solve that? Anything that, I don't know, that comes to your mind? Because there is so much diversity in topics that I think we almost are trying to solve all the problems, except that there is something hidden there that we didn't see yet.
Yeah, well, I think that, I have grandchildren, so even though I will probably die with enough energy and with enough water and with enough food, I'm very worried about climate change, and I personally believe it's quite obvious we cannot do experiments with the physical. I mean, we're doing one, but we can't do the controlled experiments. So one of the critical prey really is a merger of the 3rd and 4th paradigms in climate prediction, tuning our models with historical climate such as we have, and then trying to weigh the trade-offs in the way that we consume energy in the future. This is a challenge that the whole globe faces, and I hope that we have computers that are energy efficient enough to help us without contributing to the mess. I believe that about 3 or 4% of the world's electricity is now used in data farms. That's a huge amount of energy, and a lot of the world's fossil fuels are spent flying us around to workshops like AT-PESC. So there are, we have to invest a certain amount of the capital that we have now in energy in order to produce better ways of doing things, and that's one of the very difficult praise, I guess, for our clever falcons in the room today.
Well, thank you very much. If there is any particular question, I really want to thank you because I know how long you stayed trying to fly till here, and it's a pleasure that you have been able also, and still jet lag, but available to present remotely. Thank you, David.
My pleasure, Marta, and I hope to be there physically next year.
Yes, thanks.
Bye.